Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Because of the 2-hour early release on the A day one and the flip-flop of the schedule, we'll be recording our class period instead so that we can get the full lesson involved. Our first part of the lesson, we're going to kind of stagger it a little bit. The first part will be developing the Fundamental Theorem of Calculus, Part 2, which makes an explicit connection between differentiation and integration. We're going to come together and do a little whole group. After that, then you're going to go back into your groups and you're going to develop the calculus definition for natural log. And after you've done that, we're going to come back together for yet another whole group discussion where we'll do some examples with anti-differentiation that involve logarithms together. And then you're going to have a chance to practice. So we've got 3 different places to earn stamps. But first, I'd ask that you raise your hand if you did not get a red mark this morning. So are we good with the red marks? Okay, then let's go ahead and get started with our discussion today. I'm going to have you guys share your responses, and so please be ready. As we consider a given function f, we can evaluate f of -3 just by looking at the picture, okay? But that will get at the difference between looking for values of f versus values of f prime versus values for definite integrals. So what is f of -3? Go ahead and share. Riley, E? 2. Raise your hand if you have the same as Riley. So who had 2? For that, great. That's just the y coordinate of the function when x equals -3. Bam. What about f prime of -3? A distinctly different question. What did you get for that? Blake? 0. Raise your hand if you have the same as Blake. 0. 0. Awesome. So f prime refers to the slope of my function f anywhere along it, and we wanted to know the slope of the function when x equals -3. It looks like that occurs during a horizontal line segment on my original function f, whose slope is 0. F prime of 4, then. What did you get for that? F prime of 4. Vivian? 5. F prime of 4 is up 1, 2, 3, 4, 5. And over 2, right? So 5 halves, awesome. Raise your hand if you have 5 halves for number 3, 5 halves. That occurred during a line segment, so we could get the slope of that, right, by counting up our rise over run between those 2 endpoints on my line segment. And lastly, f prime of 5. So what did you get for f prime of 5? F prime of 5, Katie?
I said undefined.
Undefined does not exist, doesn't equal anything, so does not exist. And who agrees with Katie? Who agrees with Katie? Good. So why didn't f prime of 5 exist, Katie?
Because there was 2 different slopes. Because it was like a cusp.
Yeah, absolutely. Graphically, f has a cusp at x equals 5. There's 2 different slope values depending upon whether we're approaching from the left or whether we're approaching x equals 5 from the right. And so because the left-hand slope value did not match the right-hand slope value, right? The overall slope value does not exist. That means the overall derivative does not exist. Nice job. Let's continue on with some definite integrals. Now we're talking graphically about the area between the integrand function, in this case f of t, in between the x values -5 and -1. So we always start at the lower limit, and we scan towards in the direction of the upper limit. Everybody, let's start at x equals -5, and we'll scan towards the upper limit, in this case -1, and consider the area in between my function f and the x-axis, such that scanning from left to right, area above counts as a positive contribution, and area below counts as a negative contribution in relation to the x-axis. So it looks to me like we can just count squares or make shapes that we know like trapezoids or triangles or rectangles, and either way I get 2, 4, 6, 7, 7.5. Oh my goodness gracious. Raise your hand if you had 7.5. So you have 7.5 units. Good. Let's do another. -2 to 3. Start at the lower limit. So I'm going to start at the lower limit, and I'm going to scan towards the upper limit. So again, I'm scanning from left to right, so I'm thinking my little delta x steps are positive values, positive widths of my rectangles, and we're scanning up until x equals 3, and it looks like any positive contribution, right, towards this definite integral value from area above the x-axis will be canceled out by any equal and opposite negative contribution, right, from that area beneath the x-axis up until x equals 3. So it looks like this is canceled out by this, and it looks like then we have 2 below, so -2 is what I'm getting, -2. Raise your hand if you had -2 for number 6. -2. Awesome, Blossom. Now let's go ahead and take a look at number 7. What's different about number 7? Well, in this case, my limits, I'm starting with, my lower limit is 3. So I always start at the lower limit, in this case 3, and I'm going to scan region towards the upper limit, in this case 1, right? But now, because I'm scanning from right to left, my little delta x steps for each of my rectangles would be negative. So I'm kind of have like negative widths when multiplied by my function values. My function f is beneath the x-axis, would also be negative. Negative times a negative overall is a positive. So while we typically interpret area beneath the x-axis, right, as a negative contribution towards a value of a definite integral, because we're scanning from right to left, we'll count it as the opposite. In fact, this should be a positive value. So I get positive 1, 2, 3, 4. Is that 4? We need 4. So raise your hand if you have 4. So did you have 4 for that? Okay, great. Now we could go ahead and flip this around if we wanted to. Anytime we see that lower limit greater than my upper limit, we could always just rewrite this as the opposite of, and then flip my limits. That's the opposite of the definite integral from 1 to 3 of f of t. And then we can interpret our definite integral in the regular geometric sense. That is, now I can scan from 1 until 3 and get 1, 2, 3, 4 units beneath the x-axis, so that's negative 4. And what's the opposite of negative 4? Well, by golly, the opposite of negative 4 is still 4. Two different ways to do the problem, right? Conceptually different, but the same exact answer. What questions do you guys have about our Bellwork today? All right, so I just want to make this PDF-able. And we've got to take care of some homework. So our homework, we've got several different things to take care of. We've got our Unit 5 disc and washer packet, right? That was part of our review assignment. That was out of 8. We've got our textbook review assignment. That was out of 22. You were allowed to math 9. You didn't have to do all of your disc washer and disc. You didn't have to do all those by hand, right? You were allowed to math 9, but the setup was the key part of the review. What we're going to do is give yourself credit for those that you completed together out of 30 as a single review OTL. So I call it number R for review OTL. We're not passing in our prerequisite and skill review right now. This is only our review OTL. So our review OTL is a total of 30. And we want to make sure that we staple that together. So while we do our homework collection, I'm going to pause for Tyler Mays. Okay. All right, ladies and gentlemen, I want you guys to think back then to the Fundamental Theorem of Calculus, which shouldn't be hard to do since it was just last class that you were taking a test that asked you to state the Fundamental Theorem of Calculus Part 1. That is to say, if f is an antiderivative, right, if the antiderivative of f is g, then I can evaluate the definite integral of a function f on the interval a to b exactly and algebraically without the use of a calculator, simply by evaluating my antiderivative function at my upper limit, evaluating my antiderivative function at the lower limit, and then subtracting the two. This was our Fundamental Theorem of Calculus. Now, forever now, and after, we'll call it its Part 1, the evaluation theorem. So named because we can evaluate a definite integral using an antiderivative function. If g is the antiderivative function of f, then I can evaluate the definite integral of my function f over the interval a to b by doing g of b minus g of a. So I hope you got this on your test, right? I hope you got this on your test. Today, we're going to get the Fundamental Theorem of Calculus Part 2. Then we're going to develop the calculus definition of natural log. And so before we set up and break into our groups, I want to go ahead and point out our pre-calculus definition of natural logarithm. We know that the natural log of x is equal to y if and only if, all right, if and only if what is true. Well, think back to the definition, right? Our natural log here has what invisible base? And so we think of our common logs having base 10. What's the invisible base on ln, on a natural log? E, right? Euler's number, E. And so we could rewrite this in exponential form. Ln of x is equal to y if and only if base of the logarithm e to the exponent y, because the logarithm is an exponent, is equal to what? X, absolutely. So our pre-calculus definition for a natural logarithm is that ln of x equals y if and only if e to the y equals x. And we'll use that in the next couple of days. So today we're going to develop the calculus definition of natural logarithm. We're going to do the calculus definition of natural logarithm, and no spoiler, we're not going to erase those question marks yet, but we'll be doing that towards the end of today's class period. So our class is going to be broken up into 3 different parts. We've got a chance to earn stamps on the Fundamental Theorem of Calculus Part 2 activity. That's at 6B. If you finish your 6B stamp, then you may continue in your groups towards our second part, the 6.2 natural log activity. However, once the last group gets 6b, we're going to stop, and we're going to come back together for a whole group discussion to make sure we're good with the Fundamental Theorem of Calculus Part 2. After we have our whole group discussion, you'll continue in your groups with our natural log definition, our calculus definition. You'll get a stamp on number 5, so that's the 6.2 natural logarithms to make them different. And then we'll come back together for our final whole group discussion. And then you'll have a chance to work with your partner pairs on the practice. The practice front side involves FTC part 2. The back side involves our natural logarithm antiderivative. So we've got 3 parts today of our class period and 3 places to earn stamps. Everybody know where we're headed? Okay, then I'm going to go ahead and pause the recording and ask that you scoot into your groups at this time, and everybody should be on Fundamental Theorem of Calculus Part 2 activity. So 6.2 Fundamental Theorem of Calculus Part 2. And then if everybody could go ahead and find the Fundamental Theorem of Calculus Part 2 in their note sheet for day 1. Okay, so the Fundamental Theorem of Calculus Part 1 provided a means for us to evaluate a definite integral using an antiderivative function. So let's suppose now that we took my original function g and it was defined by an integral expression. And so we're not going to do this every time, but if I wanted to go ahead and write what g of x was equal to, I could, and I'm going to go ahead and use square brackets here. This is optional, but I'm going to go up and I want you to think through this with me. I could find an antiderivative for my integrand function, little f of t. I'll call that antiderivative function for little f of t, big F of t, the antiderivative function of little f, the integrand function. And I would evaluate it at the upper limit. I would evaluate that at the lower limit, and I would subtract the 2 in accordance with my Fundamental Theorem of Calculus Part 1. And so if I were to find an antiderivative function for little f, call it big F, I would do what? I'd evaluate at my upper limit, that's what? You can call out x. And then I would evaluate my lower limit, that is a, where a is a constant. So my original g of x is equal to big F of x minus big F of a. However, because a is a constant, the antiderivative function f evaluated at a is also going to be a constant. And so this subtraction piece, that minus big F of a, is also a constant. So if I were to differentiate my original g of x and find g prime of x, then that would be given by what? Well, that would be given by the derivative of this big F of x minus big F of a. What's the derivative, though, of big F of x?
Derivative of big F of x?
Yeah, f. What's the derivative of big F of x? Little f of x, which just so happens to be my original integrand function. My original integrand function, however, now, instead of having t's in it, I'm going to have x's in it, because the derivative of a function of x, right? Big F of x is f prime of x, which in this case is my little f of x. And so if g is given by an integral defined expression, then g prime is given by the integrand function, with the key difference that now it has the independent variable in it. This is the Fundamental Theorem of Calculus Part 2, because it makes an explicit connection between integration and differentiation. Namely, the derivative of an integral is the integrand function. The derivative of an integral is the original function. They're inverse processes, and we've used the ladder analogy, right, several times previously. If I want to find an antiderivative for a particular function, I go up one rung on the ladder. If I want to find the derivative of that antiderivative function, I would simply step back down one rung on the ladder and end up where? Exactly where I started, right? Exactly where I started. Michael?
So, like, they will always, no matter what, replace it with that upper limit or
whatever the independent variable was, will always appear in your derivative of the integral defined expression. So whatever the independent variable in g, right, is, will show up in g prime. Absolutely, just like usual. Right? Whatever the derivative of f of x is, will show up, right, with x's. When I take the derivative of a function, right, with respect to x, I have x's. Awesome. Okay, so what? Well, it doesn't matter, right? It doesn't matter what dummy variable I'm using in my integrand function. It will always be replaced with my independent variable. So now if I have a function g of m, where my independent variable is m, and I have some lower limit that's a constant, call it c. Without having to go and find an antiderivative function big F, I know that the derivative g prime of m would be the derivative of that integral defined expression. But what's the derivative of an integral? Well, the derivative of an integral should get you right back where you started. That's the original function. In this case, the key difference is that it's not f of p, though. It's going to be f of what? M. The independent variable is m, just like the independent variable in my original g of x was x. So my integrand function now has x's in it. Here, my integrand function now has m's in it. Let's go ahead and see how we can apply this when we take the derivative of an integral defined expression. So consider, please, the derivative with respect to x of an integral defined expression. Is the bottom of my limits a constant? Yeah. So it doesn't matter if that constant was -1, if the constant was 17, or if the constant is negative pi. I know that if I found an antiderivative function for my integrand cosine of t, in this case I could, right? I could find an antiderivative function, it would be sine of t. And evaluate at my upper limit, x, I'd get sine of x. And evaluate my lower limit, I'd get sine of negative pi, right? If I were to differentiate that, think in your head now, differentiating sine of x, what would I get? What? If I differentiated sine of x, what would I get? Cosine of x. In fact, I don't have to go that far and find an antiderivative function, right? All I need to do is rewrite my integrand function, but with what key difference? Well, t is no longer in my integrand function. Now simply replace the t with x. It's that easy. The derivative of an integral defined expression is the integrand function with the key difference that my independent variable now replaced whatever dummy variable was in my original integrand function. This problem you could do the long way, right? We could do this the long way by going and finding an antiderivative function and evaluating it at the upper limit. And the upper limit would be x, so sine of x, minus, and evaluating it at the lower limit would be the sine of negative pi, right, which would be 0. And then I take the derivative of that. So when I take the derivative of this, I get the derivative of sine of x is, well, cosine of x. And so we could certainly do this the long way. But I want you to know that you don't have to find an antiderivative function symbolically and algebraically in order to apply the Fundamental Theorem of Calculus Part 2. In fact, sometimes we can't find an antiderivative symbolically. Right? We can't find an antiderivative symbolically because we don't have all of our rules. And while in general it's easy to find derivatives, it's much trickier to find antiderivatives, as we'll see second semester. All right, let's consider another one. The derivative with respect to x of an integral defined expression from 0 to x of some integrand function 1 over 1 plus t squared dt. The Fundamental Theorem of Calculus Part 2 says that the derivative of an integral defined expression is simply the integrand function with the key difference that my independent variable, right, is now present. And so I could do this the short way simply by rewriting my integrand function, except everywhere I see a t, I'm not going to put a t. What am I going to put? I'm going to put an x. Right? I'm going to put an x, not a t. So the derivative of that integral defined expression is just going to be 1 over 1 plus x squared. It's that easy. But I don't want you to lose sight of the fact that this was the derivative of a definite integral, technically, right? A definite integral that I could evaluate in accordance with the Fundamental Theorem of Calculus Part 1. So if I want to do the long way, we're not going to do this every time. In fact, we can't do it every time. But for this one we can, and it's a good refresher. What would be an antiderivative function for my original integrand function? 1 over 1 plus t squared. So close. Yes, and so I could find an antiderivative function for my original integrand. It would be inverse tangent of t. And evaluate it at my upper limit. Evaluate at my upper limit will be inverse tangent of x minus evaluate at my lower limit, inverse tangent of 0. Yes? And the inverse tangent of 0 is saying what angle has a value of tangent that is 0, in this case 0 radians, and so that ends up being 0. But if I went so far as to differentiate this, took the derivative of that, and I was hoping it was gonna. It's not. If I took the derivative of this, what would the derivative of inverse tangent of x be? What? Well, the derivative of inverse tangent of x is the derivative of the argument over 1 plus the argument squared. So that would be 1 over 1 plus x squared. Is that a surprise? No, that's not a surprise because we already saw that it would simply be my integrand functions. And so I don't want to make a bigger deal right out of this than we have to. The Fundamental Theorem of Calculus Part 2 simply says that the derivative of an integral defined expression is the original function. It's the integrated function. All right. I want you to know, however, that the Fundamental Theorem of Calculus, right, Part 2, it already sounds like a big deal. It is a big deal. And it's not just an independent variable of x. We could have a composition of functions. That is, suppose we had g of x defined by the integral from a to h of x, where my upper limit itself is a function of x. Now I've got a composition of functions. And so if I wanted to find, right, the derivative of this expression, g of x, call it g prime of x, right, I would now have to invoke the chain rule. That is to say, the derivative of a composition of functions is the derivative of the overall function, evaluated at the inner function, and then times the derivative of the inner function. So for this way, one more time, we'll do it the long way. So if we were to do it the long way, we find an antiderivative for little f of t, my original integrand function. That's when you found an antiderivative for t to the 1/2. What did you get? You got big F of t, 2/3 t to the 3/2 evaluated, upper limit minus evaluated lower limit. So let's go ahead and do that symbolically. That would be big F of t if we could find one. Evaluated at upper, in this case h of x. Evaluated at lower, in this case a constant a. And I would rewrite this as big F of minus big F of. What's my upper limit? My upper limit is h of x, itself a function of x. What's my lower limit? A. If I want to go and find g prime, that is the derivative of big F of h of x minus big F of a, what would be the derivative of a composition of functions? The derivative of a composition of functions is the derivative of the overall function. What's the derivative of big F? Little f, evaluated at the lower limit, evaluated at the inner function, that's h of x, then times the derivative of the inner function. What's the derivative of my inner function? H prime of x. And so the only difference here is that we're still going to replace in the integrand function, we'll rewrite the integrand function, evaluate at the upper limit. Now we just need to multiply by the derivative of the upper limit. That is the derivative of my inner function. That's the only difference when applying the Fundamental Theorem of Calculus Part 2 with the chain. We'll see exactly what that looks like in the next examples. So once again, the derivative of an integral expression is the original integrand function. That's little f. But now evaluate at the upper limit, and then times the derivative of that upper limit. So long as my bottom is a constant, any constant. Why does this still work? Because what's the derivative of this big F at A? My antiderivative function evaluated at constant? 0. Because the derivative of any constant is 0. Let's go ahead and try some. All right. If g of x is given by the integral defined expression, let's find g prime of x. Oh, g prime of x, that's easy cheesy. All I'm going to do for g prime is evaluate my integrand function, right, at my upper limit. So this would be 3 minus sine of x squared. Everybody see it? There's my 3 minus m squared, but evaluate at the upper limit. And then what? Times the derivative of my upper limit. So I get 3 minus sine squared x quantity times what? What's sine of x? It's that easy. So it's the integrand function evaluate at the upper limit times the derivative of the upper limit. the integrand function evaluated at the upper limit times the derivative of the upper limit. The integrand function evaluated at the upper limit times the derivative of the upper limit. This is true no matter what that constant is on bottom. All right, so the derivative with respect to x of 1 to x squared of cosine of t. Do I have to go and find an antiderivative for cosine of t? No, we could, right? But when we differentiate that antiderivative function, we'll get right back to a cosine function. However, the difference will be now my cosine function will be evaluated at my upper limit. In this case, it's not just x, it's x squared. So when differentiating that antiderivative function, right, what do we need to include? We need to include a times the derivative of the inner function. In this case, the derivative of the upper limit. What's that? 2x. It's that easy. So my final answer would be given by 2x cosine of x squared. In each of these examples, we would be able to do it the long way. That is, find an antiderivative function, call it big F. That's not always the case. At this stage in our lives, do we have an antiderivative for 3t sine of t? No, we have an antiderivative for 3 sine of t, right? We have an antiderivative for 3 sine of t, but we don't have an antiderivative for 3t sine of t. We don't have a means for undoing a product at this stage in our lives. And so we couldn't do this the long way. That's okay. If we could find a symbolic antiderivative, what's going to happen when we differentiate that antiderivative? We're going to get right back to this original integrand function. So we don't have to be able to symbolically find an antiderivative in order to apply the fundamental theorem of calculus part 2. That's pretty cool. There is another difference in this problem, however. Right now, is my lower limit a constant? No, and so the first thing we'll need to do is rewrite this. This would be given by the opposite of the integral from what to what? 5 to x. Now is my lower limit a constant? Yes, so now I'll be able to do this the same as the previous slide. So this would now be given by the opposite of, and we'll evaluate my integrand function at my upper limit. So that would be 3x sine of x. And now we'll multiply by the derivative of the upper limit. Oh, this wasn't even a chain rule. The derivative of x is just 1, so I don't need to include any derivative of the inner function, derivative of that upper limit, because it's just 1. So my final answer would be negative 3x sine of x. In the interest of time, I'll just box that instead of rewriting without parentheses. There's dy dx. So the derivative of that integral of finite expression is the integrand function evaluated at the upper limit times the derivative of the upper limit. Whoa! Is my lower limit a constant? No, it's not. Gosh darn it. So I can't do this? Well, no. If I could find an antiderivative function for my integrand, in this case symbolically we can't at this stage, I'll call it big F. I'd evaluate at my upper limit. I'd evaluate at my lower limit and subtract the two. And so wouldn't y really equal this, where big F is an antiderivative of little f, my integrand function? What happens when I differentiate this? Well, because this is a sum or difference, I can simply go term by term and apply the chain rule. The derivative of big F of x squared, a composite function, would be little f evaluated at x squared, then times the derivative of the inner function. So this derivative of big F would be the integrand function, but evaluated at my upper limit. And then when I differentiate that big F, I get times the derivative of the upper limit, so times 2x. Differentiating term by term, minus the derivative of big F would be my original little f integrand function, 1 over 2 plus e to the 2x times the derivative of my lower limit. What's the derivative of my lower limit? 2. And so this is just applying the chain rule twice, and you can see the fundamental theorem of calculus hiding right there, right? You can see it hiding right there. Part 1, antiderivative evaluate at the upper limit minus antiderivative evaluate at the lower limit. When you differentiate big F, you get little f. That's my original integrand. Because it was a composition of functions, I need to now multiply by the derivative of those limits. Awesome. So we can make this look a little bit prettier, but not much. So what, 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. And those aren't common denominators, so I'll just stop there. We won't worry about that. Awesome. Okay. So we've now developed the Fundamental Theorem of Calculus Part 2, which provides an explicit connection between differentiation and integration. That is their inverse processes. I step up the ladder, I undo that by stepping down the ladder. I can undo an integration by differentiating. The next part is we need a definition, the calculus definition for natural log. Many of you have already started 6.2, the calculus definition of natural logarithms. We're going to earn a stamp at 5. It's the last one where we develop a function formula based on your stat calc menu. When you look at the graph of your stat plot, you have to select which regression would be appropriate. So we will be using the stat edit and stat calc menu for this one. Talk with your group members and decide which type of regression would be appropriate based on the appearance of your stat plot, what category of function might be appropriate. I'm going to pause the recording now, and after we've gotten our last 5 stamp, we'll come together for some natural log examples. Thank you. Okay, ladies and gentlemen, I've resumed the recording so that we can catch that, and let's add our calculus definition for natural log. So we saw a pre-calculus definition, that is, natural log of x is equal to y if and only if e to the y equals x. Well, now our calculus definition is, well, using a calculus operation, in this case integration. So we have now defined natural log of x to be, lo and behold, an integral defined expression. That is the integral from 1 up until t of the integrand function 1 over t with respect to t. So if I'm sorry, from 1 to x of the integrand function 1 over t with respect to t. That is, if I start at x equals 1 and begin accumulating area, the area in between the reciprocal function 1 over t, up until my independent variable x, wherever I so choose to stop, it will give me then exactly the value of the natural log of x. And so, what's an antiderivative for 1 over x? An antiderivative function for 1 over x is the natural log of x, with the important difference that we must preserve the domain of my original integrand function. And so while ln of x only exists for positive inputs, 1 over x exists for both negative and positive inputs, so we need to include our absolute value bars. Once again, if you think about your integrand function 1 over x, where I've got my hyperbola branches, in both quadrants 1 and 3 that exist for positive and negative x values, the natural log function, my antiderivative function, only exists for positive inputs, so we need to include the bar so that we can have an antiderivative function everywhere my original integrand function occurs. That is, we're preserving domain. That's why you need to include the bar. So we've got a brand new rule. Awesome. That means we can now find the antiderivative for these rational expressions when I have a quantity on the bottom to the first power. As I take a look at this on our note sheet, the integral of negative 3 over t plus 1, do I have a quantity on the bottom to the first power? Yes, I do. This t plus 1 is a quantity on the bottom of a fraction to the first power. This is a candidate for natural log. Why can't I use the power rule? Right? Why can't I use the power rule by rewriting this as 3 times t plus 1 to the quantity negative 1? Well, because when I add 1 to the exponent, I get 0, which is fine, but then dividing by the new exponent in accordance with the power rule means dividing by 0, and I can't do that. And so we have to use a natural log antiderivative when we have a quantity on the bottom to the first power, right? So long as the derivative of that quantity exists. What? Well, the derivative of a natural log function is 1 over the function times the derivative of the function. So I must ensure that the derivative of this function, t plus 1, exists. What's the derivative of t, however, with respect to t? Just 1 dt, and so I have no problem. This is simply constant multiplier times the natural log of absolute value, t plus 1, close bars, plus c. That's it. It's that easy. What's the antiderivative for x over x squared plus 1? Well, I do have a quantity on the bottom, right? But isn't this an inverse tangent like we did earlier in the class? Well, it would be inverse tangent if what were different about it. If it were 1 over x squared plus 1, right? Then it would be inverse tangent. This has too many x's, right? Too buku. It's got too many x's, and so we can't utilize an inverse tangent antiderivative because we've got too many x's on top. We need, so what are we going to do? Well, consider this quantity on the bottom, right, as an overall quantity of the first power. That's a candidate for natural log, so long as we can provide the derivative of that function. What's the derivative of x squared plus 1? 2x, and so that's why that x is there. It's acting as a portion of the derivative of that base, the derivative of that function, my input in the natural log. So if I had a 2 here, then I know exactly where this would have come from. This would have come from natural log of absolute value of x squared plus 1. In this case, because x squared plus 1 is always positive, we wouldn't need the bars, but we're going to always put the bars to be safe. Anytime we're using an antiderivative rule that involves natural log, we'll always include the absolute value bars from my input, except we didn't have a 2 there, so what must we do? We need to account for that fact by providing a 1/2. Now if I were to differentiate 1/2 natural log of x squared plus 1, I would get 1/2 times 1 over x squared plus 1 times 2x, and the 2x and the 1/2 we cancel each other out, and I get the original integrand function x. So we can now provide constants as well and still integrate using natural log. Oh my goodness, golly gracious. This looks like a trig rule, right, all over. How come? Well, I've got secant squareds and tangents floating all around, but it's not an overall trig rule for anti-differentiation. Instead, that's a quantity on bottom. Tangent of m is a quantity on bottom to the first power, which I know is a candidate for a natural log antiderivative rule, so long as the derivative of that quantity exists. What's the derivative, pray tell me, of tangent of m? Secant squared of m, and so that secant squared of m exists on top, right, as the derivative of that function on bottom, tangent of m, which means that an antiderivative for this is just what? Natural log of absolute value of tangent of m, those bars plus c. That's it. So what are we on the lookout for? We're on the lookout for quantities on the bottom of a fraction raised to the first power. If it's quantity on the bottom of a fraction raised to the second power, I'll use the power rule. What differentiates these from no calculus joke? What differentiates these from power rules is that it's a quantity on bottom to the first power, right? Okay. So can we do some other ones? Absolutely. This is a quantity on bottom to the first power. See that t to the first? Don't worry about that constant stuff there. I can simply grab onto that constant, -2/7, and kick it out front and rewrite so that I don't trip over it, right? I can always take that constant multiplier out front so that I don't trip over it. Now I have constant -2/7 times natural log of absolute value of t plus c. Could I do the second problem? Well, why can't I use the power rule for number 2? Right? Why can't we use the power rule for that? Yeah, because it's a quantity x to the 5th minus 6, right? We can't break that up. We can't break that up, so it's not something on bottom to the 5th power. It's not something to the -5th, in other words. It's a quantity there. Oh, but if it's a quantity, then it's a quantity to the first power. So this is a candidate for natural log, so long as we can provide the derivative of the function. What's the derivative of that function, x to the 5th minus 6? Yeah, 5x to the 4th. So if we had a 5 here, we know exactly where this came from. An antiderivative for that would be natural log of absolute value x to the 5th minus 6, closed bars plus c. But did we have a 5 there? No, so what must we include in our antiderivative? A 1/5. And so we must include a 1/5 in my antiderivative in order for that to work out. Last one, and then we'll do our closure. What's the derivative of my bottom function m cubed? 3m squared, and what do I have? I have m, right? Is this a natural log rule? No, right? I don't have enough m's on top, but at the bottom power was never to the first power in the first place. It was to the 3rd power, and so this isn't a candidate for natural log. Am I stuck then? Do I have too many m's? Well, notice how this was a summary difference on top of a fraction versus a summary difference on bottom. I can't break up this middle one, but I could certainly break this up and rewrite as separate integrals. This is the same as the integral of m over m cubed minus 1 over m cubed, all with respect to n. You see, if we break it up like that, we can now go term by term and use the power rule. That would simplify to the integral of 1 over m squared minus the integral of 1 over m cubed. And then we can integrate term by term. At this stage, I will do dot, 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 because now I'm going to say power rule, term by term. We don't need natural log for this at all. But we do need to get our closure. So for our closure today, our Fundamental Theorem of Calculus Part 1 says that if an antiderivative of f is g, then the definite integral from a to b of f of x with respect to x is given by g of b minus g of a. That's our evaluation theorem. That's part 1. That's old news. Our new definition for Fundamental Theorem of Calculus, that is part 2, if g is given by an integral defined expression, then the derivative of g, call it g prime, is simply the integrand function, but with the independent variables. So that is little f of x. Our calculus definition for natural log then relies on an integral defined expression, like my Fundamental Theorem of Calculus Part 2. The natural log of x is defined to be the integral from 1 to x of 1 over t dt, that is the reciprocal function. So an antiderivative rule now for 1 over x with respect to x would be what? Natural log of absolute value bars of x closed bars, and don't forget your plus c whenever evaluating an indefinite interval. What questions do you guys have about our discussion today? We are 5 minutes to go. Great job. Don't forget your OTL number 1. Strong work today, you guys. I'll save the recording.